Hi, guys. Well, I guess we went over that. So Title Talk is Python from space, analyzing open satellite imagery using the Python ecosystem. So this is a fun talk because I get to basically give away sweet science stuff. And you guys get to go home and use it, and you can use it right away. And so just note here that this is all up on GitHub, and like I know there's a lot of dependencies, a lot of weird stuff. Maybe a lot of you don't, have Ubuntu installed and you don't want to deal with all this stuff. So we actually have Docker instances up on Planet Scout and Notebooks repo, and you can get the Docker instance, and it's basically pretty much turnkey if you want to go play with this stuff. So it's pretty fun. Okay, so overview, this is a play in 3 parts, and I wrote this at like a software carpentry level of capability. So, as long as you've got basic syntax down, you probably should be able to pick your way through this and understand what's going on. And so the sort of, when you write a talk, you kind of think about who you're writing the talk for. So the user persona, so to speak, of who I wrote this talk for was a person who wants to use satellite imagery to do good things in the world. So like I need satellite imagery to go to my, I don't know, my town hall meeting and be like, oh, there's a thing going on at the thing, and you can see it from space. Like I said, it's all up on Git. And we're going to go through basically 3 really basic examples. So we're going to get a bunch of satellite images, and we're going to make a time-lapse GIF so we can see how a little bit of the Earth is changing over time. We're going to use OpenStreetMaps and try to figure out a bunch of stuff about a given area that we pulled down from a satellite. And then we're going to create a pretty sweet like flyover Google Earth video thing from satellite data. OK, so why should you care about satellite imagery? So I'm going to show you a few things, and this is stuff I see every day at work. So this is in eastern Peru. This may look all beautiful and verdant to you, but actually all those things up there, those are what we call artisanal gold mines. So these are where people come in with high-pressure hoses in the virgin rainforest and shoot down the banks with high-pressure hoses and then sluice it through a bunch of stuff and use mercury to collect up the gold. And this is how it grows over the course of a couple months. So this is happening right now. This is in Bolivia. So this is a sugarcane plantation in Bolivia. And this is a couple months. And like this area here, up on the right, that's like a quarter the size of San Francisco or something. It's huge. And that's just all 1,000-year-old trees that just got chopped down. This is an island basically in the South China Sea. So these islands are very interesting because they're geopolitically contested areas and China's building stuff. I'm going to stay out of the politics thing. I can tell you all that building is destroying. This is all like, everything around that is like beautiful South Pacific coral reef, and it's all getting destroyed. This is North Korea. You may have heard of it lately. This is a purported nuclear research facility, so satellite imagery can tell you a lot about this stuff. And so we sort of apparently live in this post-fact age, and like satellite imagery is actual ground truth. Like you can actually just take a picture at it and point at it and be like, climate change is not real. Oh, well, then this glacier melting over here doesn't know that. And it's pretty helpful to get your message across. And it's also useful for like search and rescue applications. So this, remember back in the springtime when it rained? That one time it rained? And it rained like a lot. Okay, so what you can see is that like it's super dry. This up in the top right corner, there's like all that brown stuff. So this is when the Oroville Dam was like almost empty. And then here's it when it's about to explode and flood all the area downstream in Oroville. And so this, like, we can actually see as the world's changing and no one knows what's going on, we can actually get an image every day and figure out like what areas are flooded and what's going on. And then the other thing about satellite imagery is it's just pretty. Like I think this is the coast of Italy. Given the weather lately, I think I'd rather be on the coast of Italy. So let's talk about what's out there for satellite imagery. So the great thing about space is that it's like this public-private partnership thing still. So a lot of the Americans put up satellites, the Europeans put up satellites, private companies put up satellites. So what you see over there are Landsat 8 and Landsat 7. So those are basically American satellites. They're super cool because they have all these different bands. So they can do all sorts of really interesting science missions. And then there's also Sentinel 1, 2, and 3, which are the European equivalents that are also really awesome. At the bottom, I have the satellites I work with. So there's the SkySat, which are these super cool high resolution. They do these super sweet high res satellite videos. The Planet Doves, which are these very, very tiny CubeSats, and we have like, I think something like 170 of them deployed right now. We're actually imaging the entire planet every day. We also have another constellation called RapidEye, which is this really cool push broom sensor that takes these huge swaths of imagery. And what's really, really cool about this from a software perspective, those top three, all the data is completely free. You could start downloading it right now. Please don't, because we're at the conference and there's already Wi-Fi issues. The ones at the bottom, there are avenues to get at this data if you would like it, and I will talk about that. So where do I get free public satellite data? Like I just said, USGS, your government, put up all these satellites, and you can just go get it on the internet. And then AWS has been kind enough to replicate most of the public satellite data out there. So you can just go, and they're just in a bucket, and you can get whatever you want. Now the question is, how do you work with it? And then I work at Planet, but we do try to give away as much data for humanitarian purposes as we possibly can. So you can basically use our tools right now to go see what's going on. Anyone can go sign up to do a free 2-week trial. So if you want to go see your house, or I don't know, look at Area 51 or do something crazy, you're totally allowed. You can get that data. It's also Open California. So everything California, you can get daily satellite imagery of San Francisco indefinitely. We also offer data for emergency response situations. We have an ambassador program. So if you're basically a grad student or work for a nonprofit, you can get at this data for free. We've also put out a few open data sets. So I just finished up a Kaggle competition. So it's 100,000 images of degradation in the Amazon, just like that one I showed at the beginning. That's all completely out there. And then some of the other satellite companies like Digital Global put out stuff in instances of a disaster. So satellite data is not like the JPEGs that you're used to. And there's some terminology that you need to know. There's some jargon when you talk about remote sensing, as it's called. And it helps to unpack the jargon a little bit so you know what's happening. So the first thing you need to know about are things like bands. So your cell phone samples in 3 bands, red, green, and blue. We're all used to that stuff. Satellites do some crazy stuff. They actually sample it at different parts of the wavelength. And they sample at frequencies way above and way below what we might actually see. So if you remember high school physics, you remember this spectrogram, this color. So your eye only samples at 3 spots there. Most satellites, like Sentinel, sample at I think 14? I got it on the next slide. Landsat, same thing. And basically, all these bands allow you to do really, really cool things. They allow you to do stuff like see through clouds, determine what plant is growing where, determine how healthy plants are, that sort of stuff. And so what it ends up is that satellite data basically is like this X-ray vision onto the Earth. You can figure out all these interesting things that you can't actually see with your eyes. A couple other bits of terminology. So there's this notion of cadence. That is to say, how often does an area of the Earth get photographed? So most of the large governmental satellites, you will try to visit most of the Earth about once a quarter to once a month. The Planet, the small CubeSat doves, those are actually getting images every day. The RapidEye, which are the bigger PlanetSats, depends. Monthly, those are tasked, so we can just send them anywhere. Similar with the SkySats, which are the Planet high resolution. With satellites, there's this notion that we call GSD. It's ground sample distance. It basically is how many meters on the ground is a single pixel. It's your resolution. So for a lot of the large governmental satellites, like the Landsat, the sample distance is something like 30 meters or 15 meters. That means a pixel is 100 feet across, almost. For Sentinel-2, it's approximately 10 meters, but it varies by band. For the doves, for our satellites, it's 3.7 meters. RapidEye, it's 5 meters. And for the SkySat, they're super high resolution, so they can see something about this big on the ground. And finally, number of bands. That's another interesting thing that you find when you're looking at satellite. So Landsat has 9 bands. Sentinel has 12. The Planet Doves have 4 bands, so we have RGB and near IR. And near IR allows us to do all this sort of cool stuff for agriculture. Similar for the RapidEye, they actually include one additional IR band, which is called Red Edge, which is used in a bunch of calculations. And SkySat does 5. So they do RGB, near, and what's called pan. When you see satellite in satellite imagery, panchromatic means like grayscale, but they sample across all the wavelengths. There's a couple other things you should know about, and this is just like dumping all this terminology to get it out of the way so it's sort of not scary anymore. Remote sensing is the fancy word for satellite imaging. People don't do satellite imaging, they do remote sensing. Orthorectification is basically this notion of when you have a satellite image, you don't know exactly where it lines up on the ground. So what you do is you take a map where you know where everything is. You take that satellite image and you run an algorithm on it. And it just basically goes and it lines everything up. This actually used to be a manual process, and now we do it mainly with computers. There's nadir angle, which is basically how far off the surface normal the satellite was swinging when it took the image. So sometimes you can take these off-nadir images. I would go Google off-nadir satellite images. They're really cool. It's like looking out the side of a very, very high airplane. Another weird bit of terminology is raster. Remote sensing people don't call things images, they call them rasters, which just makes it confusing. There's also this notion of a vector, which is, it's just a series of points. So that would be like, a vector would be the outline of a state. We all know Latin long, right, as a way of knowing about place, but there's also this notion of UTM, which is just like a slightly simplified different projection coordinate system that's used fairly often. And then there's also 2 other terms, UDM, which is a usable data map. So sometimes satellites have to deal with clouds. Funny that like the Earth is covered, I don't know, 60% of the time with clouds, or 60% of the Earth is covered with clouds. So sometimes you get this image and it's mainly clouds. So you get this thing called a UDM, and it basically says, yeah, that's a cloud, that's a cloud, that's a cloud. Don't worry about it, don't process it. And finally, there's this thing called a DEM, which is a digital elevation map. So you have Latin long, but sometimes you need to know height. So a DEM for any pixel on your image will tell you how high something is. And just to review, a raster is basically an image, and a pixel is just a point on an image. All right, so that's yapping. Who came here to actually write code? Like, I'm not going to do this for more than 5 minutes. All right, so let's write some code. So we've got 3 IPython notebooks here. They're all on GitHub. You can all go run this stuff immediately. And so I'm going to fire this one up. So I have a huge long list of imports here. I put it all together so you don't have to, and you can go pick apart what's going on here. And the only other thing that is worth noting in this set of lines here is, actually, let's make, yeah, I was just about to say, that's a little too low. Oh, yeah. All right. The other little bit here is that, you know, I'm going to work with the Planet API because we basically take all that stuff in that AWS bucket plus all our stuff, and we just put it into our API. So I have an API key here, and I'm just loading it in. So you can go and get this. It shouldn't take that long. So I'm just going to load all these imports. And so the first thing I'm going to do here is I'm going to go and make a Slippy map so I can query the Planet public API so I can get a bunch of scene or a bunch of images of the Earth so I can actually do some stuff. And I'm going to use an IPython plugin called Leaflet. And basically, it'll just pop up a Slippy map for me, and I'll be able to go draw a box around what I want and be able to construct my query really easily. And the way we do that is we construct those queries using something called Geo Jason. It's basically JSON with some concept of lat long baked into it. And so what I'm going to do is I'm going to take that map, I'm going to draw a GeoJSON object, and then I'm going to use that GeoJSON object to do a query to the Planet public API, and then I'll get some images. So let's take a look at this. This is basic boilerplate. All I'm doing is I'm saying use this mosaic server to build my maps, kind of like Mapbox. Center my image around here, zoom in, and then I'm creating basically a couple of draw tools, and I'm shoving the output of those draw tools into a little variable. All right, so I'm going to pop this. And so the goal with this notebook, as I said before, is to basically create an animated GIF of a point in San Francisco. So we're going to select the area that we're going to do this with. And I'm going to go here. Let's. I don't want to make it too big because I don't want to keep, you know, it's going to take a while if we do something that's too large. So we're just going to go kind of down here where that Salesforce tower is. And we're just going to draw a box like this. Okay, and now that we've drawn this box, what this little Slippy map has done is it's inserted the GeoJSON for this box into a local variable. And I'm going to use that local variable right here. I'm going to print it out. And I'm going to construct a time object. And then I'm going to use the Planet Public API to say, basically, I want to find all the images that have less than 30% cloud cover that were acquired this year, that are in this area, that came from those little CubeSats. So this is what PSC scene 3-man means. And then just return a list of all of these things. All right, so create an API. I have a response. And it looks like this. And it's just, oh, and I shove it into a pandas data frame just to make it print up really nicely. Because it's just a bunch of dictionaries. And so what we can see here is a bunch of information about scenes that Planet has about that location. So we can see the date they were acquired, how much cloud cover there is, the ground sample distance, the quality of the images, what satellite it came from, the sun elevation, a bunch of really useful information. There's a couple things that I need to do, though, to fix this up a bit. All of the dates that were returned aren't exactly in a date format that I can use. And plus, the scenes don't really tell me a lot about how their geometry matches up with the area I queried. So what I'm going to do is I'm going to take a library called Shapely. And inside of this query response, there's a field called footprint. And it's basically some Geo Jason that says, here's the top left, bottom right corner of where my area is. Now I'm going to make that into an object, and I'm going to compare that against my query area to see how much it overlaps. And so that code ends up looking like this. So we basically go through all the footprints in the scenes that we found. We figured out their intersection, and we shove those back into our Panda data frame, and I print it out. And so what we can see here is now we have this footprint polygon. We have a percentage overlap thing, which is something that we could use pretty handy. OK, so now that we've constructed this huge pandas data frame, it's pretty full, right? I think there's, I don't know, like 50 or 60 different scenes in here. We don't need that much data. We don't need to make a super long GIF. Some of it doesn't overlap. So what we're going to do is we're going to use pandas to basically to filter all this stuff out. So what we're going to do is we're going to create 2 new data frames from the original data frame. The first one we're going to ask for basically clear scenes with very little cloud cover that are standard quality, that were acquired after January, that overlap our input area by 60%. And then we're going to do a second batch where we're looking for even less cloud cover and even more overlap. And I'll show you why this is interesting in a minute. So we construct those, and we get these output lists. So the first one has 46 rows, and this one has 41 rows. And so now what we can do, now that we've pulled out 2 sets of data that we want to work with, we should go and visualize them and make sure that we did what we wanted to do. So I'm going to go and I'm going to just take these input scenes. And what I can do is I can take those footprint objects that I created, and I can go and plot them using Shapely over my input map. So I can see basically what I got and what it looks like. And so here, if we zoom out a little bit, we can see all of San Francisco. We can see our query area here, which is white. And then we can see the overlap of some of the scenes that we got. I only printed like the first 6 or 7. So we can see that what we're going to do is we're going to download this satellite photo, and it overlaps mostly. We're going to download this satellite image. It overlaps that much. And so we're going to go ahead and do that. Oh, actually, first, we should actually look at what we're going to get to. So inside of that query object, there's also a URL to a thumbnail. So we can peek at what we're going to get before we go and get it. So let's do that. And so this looks pretty useful. OK, so now that we've kind of queried and we figure out what we want to get and what sort of satellite data we want to use, we have to activate it and download it. So at least with the planet data, we don't have everything ready to go. There's too much of it to have ready at all times, and there's different ways people want it served up. So what you have to do is you have to activate it, and we basically take the raw satellite data and get it into the format that you want, and then you can download it. So what I've done here is I've constructed a little bit of code where you basically say, here are the scenes I want, activate them and download them for me. And you can set a couple different parameters for this. So you can set, like, I want an analytic product. So an analytic product, it'll be very difficult to visualize it if you're not sort of a GIS person. But that is actually basically, it's like the raw file you'd get off a DSLR camera. You can get a visual product, which is probably what you'll want to work with initially, which is something that you can actually see. It's 8-bit RGB. There's a couple other things you can get in there, like UDMs, which are your usable data maps, which basically tell you where clouds are, stuff like that. So what I've done here is I've constructed a couple methods. One is called getProducts, and it basically just wraps the Planet API, makes it a little bit cleaner to use. So what you can see here is that we have a method called getProducts, which basically asks the client to return the available products for a given scene and asset type. There's also activate, and then finally download and save. So this actually just makes the function call and saves it locally. And then there's a final one that are called scenes are active, which just checks that the scenes have been activated. So what we're going to do here is we're going to go through, and I'm going to take the first 20 scenes out of that list I made, and I'm going to go ahead and activate them, which takes a second. Oops. Oops, if I do this. So usually activation takes like 15 minutes. I went ahead and activated all of these before you guys came in, so I'm just kind of redoing the call here. And so we'll just wait a second. This is where I tell a really bad joke. So 2 goldfish are in a tank, and one goldfish looks over to the other one and says, "How do you drive this thing?" Oh, come on. All right. All right, so these are almost activated. Oh, so that's a good question. So that's actually a base map. So it's basically we take everything and we mush it all together and create this base map so we can kind of see what the world will look like at a certain point of time. But it's, what? Oh, what the question? How did I see that map before? And the answer is that that's called a base map, and it's something that we've composited together already that we just use for sort of web tiles. What I'm downloading here are the real deal high resolution satellite photos.
These are real time or?
What?
These are real time or?
Real time? What do you mean by real time?
I mean, at 1:22 p.m. or these were taken off?
Well, generally they're taken at about 10:30 a.m. local time because we're in a sun synchronous orbit. They're not real time. They have to get downlinked and processed and that sort of thing. All right, so now I'm just going to go and download, and because of this wrapper class that I've put in, basically it'll check if stuff I've already downloaded, and I went ahead and downloaded all these. They're fairly large. They're about 50 megs each. So we've already got everything, so we're ready to go. All right, so let's just cover some basics here. First thing you want to do, right? You have a satellite image. You want to load it into memory so you can process it. And in this case, what I'm going to use is I'm going to use this bit of code called Refugio. There's lots of different ways to do this. You can use OpenCV. You can use NumPy. I'm just doing Refugio for this case. And all these functions do is basically look for a file and drop it into a NumPy array. And they do that based on the number of channels that the image will have. We use 3 band products, so we're just going to open a simple RGB image. So what I'm going to do here is I'm just going to load those images in, and then I'm going to use matplotlib to show them. It helps if you do that. And since these guys are really, really big, you can even see that like NumPy is kind of struggling to get them loaded, or matplotlib is struggling to get them loaded. So we can see here, this is our first image, right? We can see that we got most of San Francisco, a bit out into the Pacific. Second image here, it's like East San Francisco and a good chunk of Alameda and the Bay Bridge. Great, okay. We got real satellite imagery. And these are way bigger. You can actually see the scale down here. These are 8,000 pixels across, 4,000 pixels high. So one thing that you usually want to do when you're doing imaging, right, is look at a histogram. That'll help you tell if an image is white balanced correctly and what's going on. So I've just gone here and wrote a really quick histogram method. And all this does is it breaks the channels up, buckets them, and then we can go and load them. So I'm going to do that here so we can take a look. And we can see our first image here. We can see the red channel, blue channel, and the green channel all look reasonably centered. There's also this big hump around the bottom, and that's just because we have all this, this black area, because this is actually orthorectified. But otherwise, things look okay. There's also an example here about like how to decompose the channels. So sometimes like you might want to work with just the infrared channel. Sometimes that's more interesting for figuring out crop information. So you can go and decompose images into their various channels and then remix them. And there's all these sort of GIS ag metrics that you can do by remixing those channels. And so that's what I'm doing here. Okay, so you may have noticed that like we clicked on like this little tiny bit of San Francisco here, and we've gotten this huge, huge image of most of San Francisco and the Bay Area. So you might be asking yourself, how do I clip these things down to the area I want? And so that ends up being really, really simple. What you do is you use this tool called GDAL. And GDAL stands for Geospatial Data Abstraction Library. It's a C++ library, but generally thanks, because Python is awesome, we have some swig bindings to it, and we can go use it to do a bunch of stuff for us. In this case, I'm actually going to call out to the command line version of GDAL, just because I find it usually works a lot better. And this is a fairly normal paradigm with geospatial imagery, is that you don't, since it's so large, you don't always try to process it in memory. You basically do like one small operation, dump it to a file, then do another small operation. And so what I'm going to do here is I'm going to create this GDAL command. And what it's going to do is it's going to take on that square area that I drew out in the beginning. I'm going to save that to a Geo Jason file. And I'm going to ask GDAL to take that Geo Jason file, find the area in the image that it lines up to, and then save that image as a separate file. And so I do that here, and we go and run it. And we can see that GDAL is basically saying, OK, took your Geo Jason for San Francisco, cropped it to that line from this file, and then I wrote this other file called blah, 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 _ clip. And we can go and take a look at that. And so I'm just going to load all those files again and render them in Matplotlib. And so here's a couple of them, and we can see, OK, we really did get downtown San Francisco. Here's a bunch of tall buildings. We're on the right path. So sometimes what may happen, and it didn't happen here because sometimes the images I load aren't the same as I loaded an hour ago just because I'm doing queries. Sometimes what might happen is that you only get half of an image. Remember that black area in the first images? Sometimes that you don't have coverage over that whole area. And what you might want to do is go and merge two images together to get full coverage. And so here's just a really, really quick example of that. So what you can actually do is you can feed into GDAL multiple images, and it'll actually merge them together in the order you give it, and then you can cut them out. So if you had to go fix something like that, it's really, really simple. And we'll use this example a couple times later on. And this is just going to render the same thing over again. All right, so we did all this work. I went through all the intro stuff, and now it's time to go do something fun and interesting. And so what I'm going to do is, remember how we put together two lists of scenes at the beginning? Those two pandas data frames. So I'm going to do take one, and I'm basically going to the second one, and I'm basically going to download everything, clip it all out, repeat this whole process, and then smush everything together in an animated GIF. And so let's give that a shot. And we're going to go ahead and start activating. I'm out of jokes, actually. That's probably a good thing. And so while that's activating, let's go run through real quick what's going to happen here. So once everything's been activated and downloaded, I have this list of files, right? I'm basically going to repeat that GeoJSON command to clip everything out. And I'm going to make a big long list of images, like image 0, image 1, image 2, image 3, all sorted by date. And I'm going to take all those date images, and I'm going to pipe them into something called ImageMagick. Have you guys ever used ImageMagick? Okay, so it's a Linux command line tool, and basically what it'll do for you is if you give it a list of images with sequential file names, it'll squish them all together automatically and make an animated GIF, which is kind of the currency of the internet. And it's still activating. So and the other thing to note here is that ImageMagick is sometimes nice because it's just a command line program. So again, I'm just using subprocess to call out. Oh my God. Okay, we'll hold off on this for a second. We'll come back. I'll get going on this next tutorial. Just because we're going to be pressed for time. So second tutorial, right, is, OK, we've kind of mastered the basics of getting satellite images, loading them, and looking at them. Now we actually want to figure out where things are in the world. So what I've done here is I've basically put together a couple tutorials using OpenStreetMaps. And what I'm going to do is, this is the same set of imports as before. And the goal of this tutorial is basically to go and look at all the parks in San Francisco and figure out what is the greenest park, so that when we want to go out, when it's sunny and hopefully like a month, we can find the greenest park and actually go there and have a good time. So I'm going to repeat basically the code that we had before. So I'm going to go load this mosaic. And this time I'm going to go ahead and sample a bigger chunk of San Francisco, because we're going to look over the entire city. Now I do that. Now I'm going to repeat the queries that we did before. And basically, I'm processing for the same thing. I'm going to basically find a set of images that'll cover most of San Francisco, and I'm going to put them together into a big mosaic. And so once I've actually done that, I can see the scenes that I've queried, and I can see that I have pretty good coverage over the city. And so I'm going to reload our activation and download code, and I'm going to go and spin these scenes up. And now while I'm waiting for that, I'm going to come back over here, and we're actually going to run this. And so what you can see here is that we're clipping out all our files. And now it's running the last command. And what I can do is I can go back over to my console. And I can load this thing up. And what we have here is a time lapse of downtown San Francisco. And this is basically since January. And so now, like basically with this tool, right, you can go to anywhere on Earth and actually produce a time lapse of what was going on. Okay, so back here, meanwhile, back at the ranch, we've activated all these scenes. I can go ahead and download them. And now we can actually go to start dealing with OpenStreetMaps. So OpenStreetMaps is this huge and open collection of data about the Earth, and it's absolutely free to query. And the interface is like super powerful, but it's also super cryptic. So I'm not going to get too deep into that. But what we can do is if we have a pixel in a satellite image, and we want to know where that pixel corresponds, like what is underneath that pixel, like what building, what street, what state, OSM is a great way to figure that out. And so there's this API interface called Nominatum, and there's Python wrappers for that. And we can basically look up like if we have a lat long or a UTM position, we can basically look up what's underneath it just like Google Maps. And so I'm going to show you how to do that. And basically, this query interface works with lat and long. So what we have to do is figure out how to take a pixel in an image and change it into a lat and long position. And the way we do that is a little bit backwards, because what we're going to do is we're going to get a pixel, translate it to a UTM coordinate, and then we're going to translate it into a lat long coordinate. And so what I'm going to do here is I'm going to open my file, and I'm going to call this. I'm going to call the Python interface to GDAL. I'm going to open up the scene. I'm going to get this projection reference, and the projection reference, along with a geotransform, will allow me to figure out what UTM zone I am and do that UTM transfer. And so let's take a look at this. And so what's come out of this is basically the scene's projection. And I can see that inside of here, it's in UTM zone 10N. And I need that information to basically get the lat long. So to get the lat long, I basically take that geotransform object that I got earlier. And it's basically an affine transform, which means you do a bunch of linear algebra between your pixel and your lat long. And I'm also going to write a function here that's called drawPoint, which just takes an input image and draws a point on it. So we're going to run these. And so now what I can do is I can open up a scene, translate a pixel to UTM, translate that UTM to lat long, and then I can use the Nominatum API interface to go and query that and get the address for what's underneath it. So I've set up stuff here where I just say, I want pixel 7,000, 1,400, and I'm going to run a query really quick. And so I did just a query on a pixel in my first image that was at 7,000, 1,400. And I get, it's called Skyride, Mark Street, Oakland, Alameda County, California, blah, 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 blah. So for completeness, I think we should actually take a look and make sure that this seems like it does what it's supposed to do. So what I'm going to do here is I'm going to basically load my image, annotate my pixel position, and then draw what I got out of the OSM interface on top of it. And so we can see, oh, it's pointing to a spot way out here. I'll believe that. I believe that's Alameda County. Okay, so now that we can kind of query positions, the next thing that we'll want to do is actually start building up our map of parks in San Francisco. And the way we'll do that is we'll be querying an OSM interface called Overpass. And the Overpass query language is really, really, really cryptic, but if you do a bit of Googling, you can basically find the query that you want. So I've constructed a query here that basically gives me all the parks in a given area. And what I can do is I can run, there's actually a web client for this, and I can run a query over all of San Francisco and get every single park that is in San Francisco and then save it as a Geo Jason file. So you can see here, I already ran this because it takes a few seconds. And you can see, just like Google Maps, it's sort of highlighted all the parks. And then what I can do is I can export this as Geo Jason. So I already did that. And what I can do is I can then load this into GeoPandas and take a look at all this park information that I've gotten. And I'm going to go ahead, and then I can sort it on certain parameters. So I can sort it on area. I'm going to go ahead and do that here. There's other really cool stuff inside of here. So you can actually go and like query Wikipedia information, which can be kind of handy. And so I can see that there's some information in here. I can see that there's you know, the geometry of all the parks. There's some information sources, but really what I want to do is actually I want to see where all these parks are sort of in my notebook as I'm working. So what I can do is I can take the GeoJSON that was encoded in these objects that I got back from OSM and then plot it back on my Slippy map, which is fairly simple. I just create this object and I pass it to the map, and it'll load up. Okay. So what we can see here, we have a big query area, we have a bunch of park outlines, and we have the scenes that intersect them. So what I'm going to do really quick is I'm just going to quickly sort out my parks by how large they are and take a look at the data associated with them. Okay, and then we're going to actually get to the meat of this problem. So I said at the beginning what I wanted to do is sort and find the greenest park in San Francisco. Well, how am I going to calculate that? The way I'm going to calculate that is I'm going to take that example that we did before. I'm going to take every single park that I queried. I'm going to use GDAL to make it into a little tiny clipped out image of that park. And I'm going to load it and use basically NumPy to calculate the greenness over the other two channels across the entire park. And then I'm going to load that into the data frame. So then I can actually tell how green every single park is. And you can, so this is basically the code that runs that. There's a function that basically takes that GeoJSON, huge GeoJSON file that I got back from OSM and saves it as smaller files. And then this command is very similar to what we had before, where I take our input scene and I crop it out into a smaller image. And so we're going to put it all together here. We're going to go through our entire list of parks. We're going to write the GeoJSON. We're going to crop the scenes to GeoJSON, and we're going to save them out. Now it looks like this, and it just trucks along. And we can see this. So these are all still geotiffs, which are big and huge. And there's a little bit of a trick if you want things to be a little speedier when you're loading stuff in your notebook. And that is to use ImageMagick again to convert it over to a PNG file or a JPEG file. Makes it a lot easier to see. So I'm going to do that here, and we're going to take a look at our little parks. And so what we can see is these are various parks around San Francisco, all cropped out from the satellite imagery. So let's see if we can find one that looks super familiar. Anyone know where this is? Fort Mason. So now I'm going to go and actually write our analytic code. And there's better ways of calculating crop greenness. And it's a technique called NDVI. We're not going to go over that because you require an analytic product. So all we're going to do is we're going to take the two channels that are on the two images, and we're going to run, or the three channels, divide the green channel by the other two channels, sum up the results, check that that the pixels are actually pixel values and not black areas, and we're going to save that result. So we run this, and we're going to map our greenness function over all of our scenes. And then we can go and plot each of our parks by how green they are. And so now we have a plot. And we can see here, actually, so the highest greenness park that we've been able to calculate out of this data was Debauchee Dog Park. Then there's a couple other ones, Midtown Terrace Park, and they're all sorted by greenness. And so what we can do is we can actually take that greenness data, or actually what we can do is take a look at what the data is telling us. And so we can see that, like, okay, this park looks super green. And as we scroll through our list of parks, they should get successively less green. And what we can do is we can also take that data and our input Geo Jason and then plot it back over our Slippy map. So we end up getting something like this. And so, okay, Presidio is very green. This park looks, this is Golden Gate Park, looks very, very green. Some of these ones out in the hills might be a little bit drier, a little bit less green. Okay, so API activation took a little bit of our time. We got 5 minutes left, so I'm going to go through this guy really, really quickly. So this is, again, the exact same thing. In this example, what we're going to do is we're going to go and make a big, take a large sample of San Francisco, build a satellite image for that, and then we're going to build a movie by basically cropping out a small region in the image following a path that we wrote in GeoJSON. And it's going to go crop, 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 crop all the way across it. And we can smash those all together to build a video. So basically we can do a video, we can roll our own video flyover of a given area. So I'm going to pull this all together. We're going to start with the same Slippy map. And I'm going to say, I want to query scenes from this area. And I want my path to go like this. And what I'll do is I'll query our API again. We've all seen this already. I'm going to filter out our scenes. I'm going to go and just check that everything's OK. And we see we get a bunch of scenes overlapping. Sort and activate the products. And this is the time-consuming step. And once that's done, we'll get into the meat of the program. So first thing I do here is remember that mosaicing call I made earlier? Same thing goes on here. So the area that we're looking at is too big for one scene. So we're going to take all those scenes we downloaded and press them into one giant image. And that's what this is doing. And it's this exact same call from GDAL. So let's download everything. And we'll download all of these. And what we end up getting is a giant scene that covers most of San Francisco. And from this, we can actually build our movie. And it looks like this. So first thing to make this all work is we write a really simple crop function. And this crop function works by taking the center and a width and height and cropping out the scene to that specific area. So you just say, at pixel position 1010, give me an area that's 640 by 480, and save it. So I'll run that. And we'll check that that works. And it does. And so here's the actual most difficult part of all that. You saw at the beginning where I clicked on that GeoJSON path. I need to basically do the reverse of the problem that we just solved. And that is to say I need to take a Latin long and convert it to a pixel position. And the way we do this is really, really simple. We take the corners in Latin long of our image, and we take how wide and how high our image is, and we basically interpolate between them. And it's really that simple. And that actually gives us a really, really good approximation. So I do that here. Reprojection. And I need to pull out a couple little parameters to get the corners of the image and do the conversion. And then I finally write this function. And so what I can do is I can actually check that now I can convert those GeoJSON points to points on my image. And what should happen here is that path that I drew, I should get the points that I clicked. And I can see that that works. So now the next step is, instead of having just the midpoints that I put, I need to basically figure out all the pixel positions in between. Because what I'm going to do is I'm going to interpolate and crop out at every single position in between those start and stop points, save them as files, and string them all together in 1 minute. All right, ready? So I'm going to go interpolate all those waypoints and do the scene builder. And basically, I can show that the path that I had before, that thing that I drew on the Slippy map, is actually what's showing up in my scene. So this should work, in theory. And so I'm going to call this call that does the interpolation, does all the crops, and saves all these images. And so this will take a second. And what we should see here, because it's dumping them all to a file, is we should see a pile of PNG images coming out. And so this is done. And what we can do is we can use AVCom, which is kind of like ImageMagick, but for videos. And I can take this AVCom call. And use it to smash all those images together into a video. Oops. And so it's smashing all those things together. And what I can do is then I can use VLC to open up that movie file. And so we now have a flyover movie of San Francisco. That's all I got. And so I went a little long there. I apologize. I can answer questions afterwards. I'll be here all weekend. But Noah's got to go. I'm sure he's got to. Oh, he's chill. OK, maybe one question. Yeah. Oh, OK. Well, yeah. Submit an issue, and I will take care of it.
Is all the processing done on the laptop just now, or done
Yeah.
in the cloud?
It's all done locally. I mean, there's no reason you shouldn't be able to do all of this locally. Maybe one more? Is the brightness normalized through the API? That is an actually awesome question. So no, the brightness right now is not normalized. That we have a nominal color curve. There are examples in that notebook repository to do like top of atmosphere, bottom atmosphere, and reflectance calibration. So they're parameter files that you can pull out, and you can do that. Yeah. Cool. Thank you, guys.